A dentist uses a curved mirror to view teeth on the upper side of the mouth. We all have seen that, didn't we? Well, suppose she wants an erect image with the magnification of 2 when the mirror is 1.25 centimeter from the tooth. So let's identify what is our object. So the tooth is our object. So therefore, this 1.25 centimeter is the distance of the object from the mirror. So I'm gonna just immediately take out the information that I have. Distance of the object is 1.25 centimeter, and we also read that wants the magnification to be 2, which means M should be 2, and also the image should be erect, which means it has to be positive. Magnification has to be positive 2. So, and that means the erect means it also has to be a virtual image. So let's call it virtual. Okay. And let's continue reading. Treat the problem as though the object and image lie along a straight line. Well, of course, it is very important to treat like that. So now the questions are, so we have A, what kind of mirror, concave or convex, is needed? So let me write it here, concave or convex. Use a ray diagram to decide without performing any calculations. B, what must be the focal length and radius of curvature of this mirror? So we want to have a B, focal length and radius. So we want to find out focal length is a question mark, radius is a question mark, and C, draw principal ray diagram to check your answer in part B. Okay, well, let's start with part A. So we want to start with trying out, well, concave mirror. Okay, so concave. To see what is, how can we construct. So let's suppose that you have a principal axis. Here's the concave mirror and the shiny side is inward. Okay, so which means the focal length. So if I imagine this to be the center of the curvature, this should be the focal point. So we have different situations. We could have our object to be beyond the center, right here. We could have our object to be between the center and a focal point and before the focal point. Well, let's do diagrams for each of them. So let's start with first one, which is the distance of the object is further away from the focal central center of the curvature. Then we need only at least 2 rays. Let's do the parallel ray, which will go hit the mirror and reflect back to the focal point. Okay, and then we would have a central ray which will go ahead and hit the mirror and come back. So then we would have an image that is formed right here where the 2 reflected ray meet. So this would be our image and this is our object. So clearly this situation is no use for us because the image is reduced and invert it. So let's try a different situation now. We are going to draw again the principal axis and then the mirror again. Suppose it's the same. So here is the central point, here's the focal point, and this time our object is between the center and between the focal point. Let's go ahead and then draw our parallel ray, which hits the mirror and comes back to the focal point, towards the focal point, and then the central ray, which is let me use a different color here, which has a direction of the center, and it hits the mirror and then comes back, passing through the center. Okay, now we have the image that is magnified, but it is not erect, it's inverted as well. Okay, we have one more situation to discuss. Let's draw again our principal axis or optical axis, the mirror, concave mirror, and then we have the focal point and then the center of the curvature. And now our object is before the focal point. Now we're going to use the two rays again. So the parallel ray is going to hit the mirror and come back towards the focal point, reflected ray, and then the other one will be the central ray, which has a direction of the center, hits the mirror, and then reflects back and passes through the center. So obviously these two are not connected, so they can actually go to the other side of the mirror and be magnified. Wow, and virtual. So now we get the image that is erect, and it is magnified. Okay, so this is the object, this is the image. So it seems like this is the correct thing that we want, but let's try to check also the convex ones. Okay, so see what we will get in a situation of a convex mirror. So I'm going to use the other side of the mirror, so we can the other side of the concave mirror, so we can compare with each other. Okay, now we have a principal axis, we have a convex mirror where we have, let's say this is the center of the curvature, this is the focal point, and the object is, let's say it's a one focal length. We're going to try different ones, one focal length, two focal length, three focal lengths, and see what happens. Okay, so DO equals the focal length, for example, and then let's use our parallel ray, which is hitting the mirror and has to reflect in a way so the direction is towards the continued towards the focal point. And the next one is the central ray. So I'm gonna have the ray hit the mirror towards the direction of the center because it's gonna come back and continue on. So the two rays will meet each other at point here behind the mirror. It's erect, but it is reduced, so not our case. Let's try one more example. Now let's put the object 2 focal lengths away from the from our convex mirror. So here's the focal point, here's the center, and then so one focal point, a focal length, 2 focal length, and then let's put them image object right here. So this is our object. Use our parallel ray, which has to again meet at the focal point when it is reflected. So this is the reflected ray, this one is the incident ray. Now let's do the central ray, which is going to go this direction. Okay, so now we have again our image is reduced and virtual. Okay, so but it is reduced. We want a magnification, correct? Now one more time. I know it's kind of clear already that the convex mirrors are not the best, but let's put a little bit more further away the object. So here's the mirror, the focal point, the center, and then let's put the object really far away. Okay. And then use our parallel ray, which meets, which has to continue to meet the focal point. And then the central ray, as you can see, the central ray is gonna be really make the image very, very small. Here's our image. So right here, this is where very small and very very virtual, although it's erect. The only place where you can get the only time when you get the virtual image and erect, it is when you have a concave mirror and you have the curvature in a way that the object's distance is way smaller than the focal length. Okay, now let's go ahead and do the second part of our problem. Let's see what it is asking us to do. Well, in part B, we're asked to find the focal length and the radius. So what we know that about the spherical mirrors, we know pretty much that 1 over f equals 1 over the object plus 1 over di. So we could find the focal length if we had the distance of the image, but we don't have it. We only have distance of the object. Now our goal is to find distance of the image. So to find that, we're going to use the magnification, where magnification we know equals negative distance of the image over distance of the object. So in this case, we have everything. So the distance of the image equals negative m times distance of the object, which equals negative 2.00 times do. So I want to plug this one into here. Okay, well, let's use a little bit more space here. So I can say 1 from here. I can say 1 over f equals, let's put in this way, dO di on the bottom, dO plus di on the top, and then plug the di into here. So we have a dO plus negative 2.00 dO divided by dO times negative 2.00 dO. So this makes it equal. So we have negative dO on the top and negative 2.00 dO squared on the bottom. So one of the dO's will cancel. We'll have 1 over 2.00 times dO. So to find the focal length, take the reciprocal from both sides. That equals 2.00 times dO. Let's plug in the numbers. So our dO equals 1.25 centimeters. That equals 2.00 times 1.25 centimeters, which equals 2.50 centimeters. Having a positive focal length, it already tells us that it is a concave mirror. So that positive allows us to tell. Now the next part is the finding the radius of the focal of the curvature. So we know that the radius is a 2 times the focal length, which will be 2 times positive 2.50 centimeters, and that is a positive 5.00 centimeters. Okay. Finally, the last part of the problem tells us draw principal ray diagram to check your answer in part B. So let's try to see what we have in here. We said that we have a concave mirror because it's positive 2.50, right? So let's say the focal point is right here, and from here to the vertex of the mirror is 2.50 centimeters. Now our object is 1.25 centimeters away, which means so really halfway from the focal point. So here's the object, okay? And we already know what we get for this situation. So this would be 1.25 centimeter. Now let's use our ray diagrams again. So we'll just do the parallel ray, which will reflect in a way that it will just pass through the focal point. Okay, so this is the direction I chose. Okay, so here's the focal point. And then finally, the central ray. My picture is really very bad in here because I'm using approximation. And let's also put the center right here so we can make a better analysis. Hopefully this works. Now, the central ray would be from, that is a center, hits the mirror and comes back to the center. They never meet, but if you continue these two rays until they meet, they will meet on the other side. And guess what? Our image is about 2 times of our object. So here's how we verify our solution, a mathematical solution, which we already figured out in the beginning when we were choosing what kind of mirror we have. That situation right here. Okay, thanks for watching. Stay tuned for more.